Previously, we covered the core foundations. Now in part 2, we tackle Main Asteroid Belt, formation history. Last time, we looked at what the Main Asteroid Belt actually is, its location, its scale, and what it contains. Today's question is this: how did it form, and why does it look the way it does? That might sound like a historical footnote, but it isn't. The answer shapes everything we understand about how the inner solar system, including Earth, came to be. The main asteroid belt sits between Mars and Jupiter, roughly 1.7 to 3.2 astronomical units from the Sun. It's a broad, donut-shaped region containing hundreds of thousands of rocky and metallic objects, plus millions of smaller fragments we haven't individually catalogued. But here's what immediately stands out when you study it. The belt isn't evenly distributed. It has gaps. It has distinct zones. It has families of objects clustered together in ways that cannot be random. All of that structure tells a story, if you know how to read it. And that story begins more than 4.5 billion years ago. In the earliest phase of the solar system, the Sun had just formed from a collapsing cloud of gas and dust. What remained around it was a rotating disk of material, the protoplanetary disk, dense enough in some regions to clump together, too thin and too disturbed in others to hold itself together for long. In the inner solar system, rocky planetesimals, bodies ranging from a few hundred meters to hundreds of kilometers across, were colliding and merging. That process eventually built Mercury, Venus, Earth, and Mars. The asteroid belt region, sitting further out, should in principle have gone through the same process. The raw material was there. The physics was the same. So why didn't it? That's the open question at the heart of this episode. And the answer, it turns out, involves the largest planet in the solar system, and the possibility that it behaved in ways we once assumed it hadn't. Jupiter is the key. It always has been, in asteroid belt research. A planet more than 300 times the mass of Earth generates an enormous gravitational field, and that field reaches well beyond its own orbit. As Jupiter formed, and it formed relatively quickly, within the first few million years of the solar system, its gravity began stirring the material in what would become the asteroid belt. That stirring did two things. First, it prevented planetesimals in that region from accreting efficiently. Every time a body tried to grow by merging with its neighbors, Jupiter's perturbations increased the relative velocities of those objects. Instead of gentle collisions that could build mass, you got high-speed impacts that shattered things apart. Growth was disrupted before it could reach completion. Second, Jupiter's gravity established a series of orbital resonances throughout the belt. These are positions where an object's orbital period is a simple fraction of Jupiter's. For example, an object at the 3-to-1 resonance completes exactly 3 orbits for every one Jupiter completes. At those positions, the gravitational nudges from Jupiter add up predictably and repeatedly, and over millions of years, they push objects out of those orbits entirely. The result is what we call Kirkwood Gaps, named after the American astronomer Daniel Kirkwood, who identified them in 1867. Real, measurable absences in the asteroid distribution, carved out by Jovian resonance and maintained to this day. The belt structure isn't just about gaps, though. It's also about composition, and this is where things get more complex and considerably more interesting. There are distinct zones. The inner belt is dominated by silicate-rich S-type asteroids. The outer belt is dominated by dark, carbon-rich C-types. Between and beyond these, you find M-types, primarily metallic, and other rarer classes. That compositional gradient roughly mirrors the temperature gradient of the early solar system. Closer to the Sun, it was too hot for volatile compounds, and ices to condense. So you get rocky, refractory material. Further out, cooler temperatures allowed carbon compounds and more complex chemistry to survive. Here's the complication, though. The distribution isn't perfectly clean. C-type asteroids appear in the inner belt. S-types show up further out than a simple model would predict. Some objects seem to have originated elsewhere entirely, possibly from beyond Jupiter, possibly from the region that's now the outer solar system. Which brings us to one of the most significant ideas in planetary science of the last 2 decades. Around 2005, a group of researchers published what became known as the Nice model, named after the city in southern France where the work was developed. The proposal was striking. The giant planets didn't form in their current positions. They migrated. In the Nice model, Jupiter, Saturn, Uranus, and Neptune were initially more tightly packed. Gravitational interactions with a disk of planetesimals beyond Neptune caused them to shift outward, and in Jupiter's case, also inward. When Jupiter and Saturn passed through a 2-to-1 orbital resonance with each other, it triggered a period of intense gravitational chaos throughout the solar system. That's thought to correspond to the late heavy bombardment, roughly 3.9 billion years ago, when the inner solar system was repeatedly and severely impacted. During that migration, Jupiter's shifting orbit would have scattered material across enormous distances. Some objects from the outer solar system were driven into the belt. Some belt material was ejected entirely. What we're looking at today is, in part, a dynamically processed remnant, not simply the material that was always there, but a mixed population shaped by billions of years of gravitational sorting. A more recent extension of this thinking is called the Grand Tack hypothesis. It proposes that Jupiter actually migrated inward, toward the Sun, before being pulled back outward by Saturn. That's a hypothesis, not confirmed, but if it happened, it would explain several features of the inner solar system. Why the belt is so depleted in mass compared to what accretion models predict, and why Mars is smaller than it probably should be. On its inward sweep, Jupiter would have cleared and scattered a substantial portion of the material that might otherwise have fed Mars's growth. The belt we observe today contains roughly 4% of 1% of Earth's mass. That's a tiny fraction of what was likely present early on. Most of it was ejected by Jupiter. The rest was consumed in collisions or incorporated into the terrestrial planets. What remains is the residue. And that residue is scientifically invaluable. Because the belt was never incorporated into a large planet, it preserves material from the early solar system in a relatively unprocessed state. Carbonaceous chondrite meteorites, which originate from C-type asteroids, contain pre-solar grains, particles that formed before the Sun itself existed. They carry chemical signatures that have survived more than 4.5 billion years. NASA's Dawn spacecraft, which orbited both Vesta and Ceres in the 2010s, gave us detailed surface geology, elemental composition data, and gravity maps of 2 of the belt's largest bodies. Ceres turned out to have water ice beneath its surface and bright sodium carbonate deposits at Orcator Crater, evidence that geological and possibly hydrological processes shaped it long after formation. Vesta showed signs of differentiation: a metallic core, a mantle, a crust. 2 bodies in the same belt, formed from similar raw material, with dramatically different internal histories. That diversity is itself a clue. The belt isn't a uniform collection. It's a sample archive of the different processes and environments that existed in the early solar system. Next time, we look at one of the most persistent myths in planetary science, the idea that the asteroid belt is a failed planet. It's a reasonable assumption. It's also wrong. And the reasons why tell us something important. The full Main Asteroid Belt series is in the playlist, and episodes 1 and 2 are a good place to start if you've just found this channel. If you find this kind of science genuinely interesting, subscribing means you won't miss the next episode when it goes up. No algorithms to wrestle with, just the next part of the story when it's ready. That is part 2 of Main Asteroid Belt. In part 3, we explore the next key question. Subscribe so you do not miss it.